A very happy and pleasant morning to all. I am Ms. Devibala Saraswati, Assistant Professor, Department of PG Physics, GTN Arts College, Dindigul. On the behalf of our PG Department of Physics, GTN Arts College, I welcome you all for today's session on Becoming God, a chronicle of human endeavor on space, matter, and time. First of all, I would like to express my heartfelt gratitude and sincere thanks to our respected Secretary Dr. 9K Ratnam sir, our beloved Director Engineer Durai sir, and our esteemed Principal Dr. P. Balagurusamy sir for your constant support and guidance to organize such events in our college. Now, I'd like to introduce our chief guest, Dr. P. A. Praveen, postdoctoral fellow, Indian Institute of Science Education and Research, Tripadi, with great pleasure. He received his doctoral degree in 2019 in metal organic nanostructures for thermo-optical applications. At present, he is a postdoctoral fellow at Indian Institute of Science Education and Research, Tripadi. His significant achievements are as follows. He received Research Fellowship Award from IISCR Tripadi, India in 2019. In 2017, he got the Best Paper Award in 21st National Seminar on Crystal Growth and Application at National College, Trichinopoli. In 2014, he received Research Fellowship for Meritorious Students in Science from UGC, India. In the same year, he got the Best Paper Award in National Conference on Computational and Experimental Physics of Functional Materials at KSR College, Trichandur. He has published 10 research papers in the reputed international journals and he has authored and co-authored 3 books. With this brief introduction, I welcome our today's chief guest, Dr. Praveen sir, on the behalf of our PG Department of Physics and GTN family. Now, I'm very happy to inform that we have received more than 500 registrations for this event. I welcome each and every participant to make use of the session. Before going into the session, I would like to suggest few instructions to the participants. The speaker will be taking first 45 minutes and then the remaining 15 minutes will be allotted for the query session. So the participants are requested to ask the queries or question in the chat box only at the end of the presentation. I kindly request the participants to please keep it very professional and only ask questions related to the content of the webinar. Please avoid greeting messages like welcome, good morning, and avoid mentioning your name and institution address, etc. Feedback form is already sent to your registered mail and Telegram group. The form will be open only at the end of the presentation. We are streaming this webinar on our official Facebook page also. So those who could not enter into the Zoom page can access our FT page for the info. We are having a separate team to filter the questions which will be answered by our speaker, Dr. Praveen sir. Once again, I welcome you all for this session. I hope we're gonna enjoy the session for the next 1 hour with our speaker, Dr. Praveen sir. Over to you, sir.
Thank
Thank
you
you.
for the nice introduction. At the outset, I wish to extend my sincere thanks to the management of GTN Arts College as well as the faculty of PG Department of Physics for your invitation to present a talk there. Especially, I'm very thankful to Dr. Jodh Murugan. He's just a mentor to me and always guide me in my hard times. So I'm very delightful to present a talk in his college. So today we are going to see a chronicle of things that humans have achieved so far over the last 2000 years. This is in particular concentrating on the physical laws that developed over time and how they influenced different aspects of our understanding towards this universe. So when I put this title, I received some messages from some of my friends. So you are saying like humans are becoming God or humans are much better than God, something like that. So okay, we will see the answers for such questions here. So in the outset, we will see some of the things that starts the quest for search for the eternal knowledge. and some of the giants are there. You might have saw the bird standing on the shoulders of giants. If you are a researcher, you might have saw such a line in the Google Scholar webpage that has been actually mentioned by Newton, mentioning Galileo Galilei for his achievements. So it's true, actually, even nowadays we are standing on the shoulder so that we can look into the much farther distance, then we can actually look into our normal vision. So we will see some of those great people and their uh, achievements as well as their limitations. Also, we would see some of the interesting theories like general relativity and quantum mechanics. I hope if you are a physics graduate, ultimately you might have known these theories. So we will see the importance of these theories in understanding our understanding towards the universe. Ultimately, both the relativity and quantum theory, even though explain things about the universe, they are not in agreement. It means some people or some scientists are arguing either one should be right. So there is a question. The recent 1 or 2 decades is there is a possibility to unify unify these two models, and so that we could have a grand unified model. So we would see all those things in the following slides or during this talk. Uh, so let's start with the questions. I hope it's a normal thing as a human, or questioning is what makes us human. So because even during as a non-developed and hunting gathering community, humans are always curious about the different things. They ask questions, and somehow they theorize their understanding. They compare the things, so that questioning is the basic capability of a human that leads us to this particular stage, I hope, because at least as far as our animal kingdom is considered, we are or hopefully, we are the only animals who are questioning, reasoning the things that around us. So, as a normal person, you might have wondered at some stage. So, if you look into the sky, you might have wondered why there are so many stars there, why there is a moon, and why the moon is growing, and there is some empty moon day, and why the sun rises and sets. So even as a child, we might have wondered all those things, and gradually we might have get the knowledge about these things over our when we grow up. We would know stars are nothing but our sun, which is far from away, and sun is also a star which is around 8 minutes distance from us. Since the Earth is revolving around the sun, there is a feeling like the sun is rising and setting, and moon is a satellite of our Earth, like that. So these are the things we gathered over and over days. So nowadays, even if you ask a kid, what would our Earth looks like? The kid may easily answer. So it is a globe. It is a spheroid. I have saw that in a video or in some satellite image like that. But interestingly, as our ancestors around 2000 years ago itself, they have no that Earth is a spheroid or a globe. Their reasoning is very interesting. For example, if you look into the Greek Chronicles, Greeks know well that Earth is in spherical shape. But their reasoning is something like that. You might have known in ancient days they have used the North Star to used as a direction point. So if we move towards the North Star, it will gradually rise to the to above your head. So at the North Pole, the star is exactly on the center point of or in the center of your vision. So that this is possible only in the case if the earth is a spheroid. Otherwise, if it is a plane or a spherical plane, it is not possible. At some point, even whatever the distance you are moving, the star also moving, and the vision, the direction of the star is also not changing with respect to our movement. And one another interesting thing is when they have watched the ships arriving the shore, they have seen that the top of the ship appears first, and the bottom of the ship appears at the final stage of the ship enters into the vision of a human. This is only possible when we have a spheroid, because only in the case of a spheroid, the top would appear initially, and vice versa. They have also one another interesting thing, if we look into the solar eclipse, it appears always that uh, moon fall behind the earth and sun. This is possible in the case if both sun, moon, and earth are plate-like structure. The interval should be equal, but that is not the case in the case of solar eclipse. They appear at different times and different intervals of an year. So obviously, this would happen only in the case that only possible if both the moon and earth or spheroid shape. Of course, sun should also be spheroid. So this knowledge is almost, it seems, universal at those days. For example, even if you look into our Indian scholars, some Tamil teachers argue that Thirulluvar also know that Earth is round in shape. He has mentioned something like "Sulandrum Yerpinadu Ulagam," something like that. So it means the Earth revolves around itself, like that. So they argue that even in those days, in third century Common Era, people might have known that Earth is round in shape. Of course, you might have heard a lot of stories about Aryabhatta and Bhaskaracharya, so they know they are the well-known astronomers of Indian history. But one another interesting thing probably you might have not known is Andal. She is a woman poet, lived around 9th century Common Era. In one of her verses, she mentioned something like Vyalan Murangi Velli Elunditru, something like that. It means Jupiter. She mentioned something like Jupiter and Venus, and using this fact, scientists have literary people have estimated the time of her time, and that's how they estimated her age as 9th century CE. So it may we may conclude that almost all the civilizations and cultures almost know the earth is spherical in shape over the time, but there appears
Excuse me, Praveen sir. Excuse me.
hello. Yeah.
Excuse me, sir. Sir,
Yeah.
can you make it little louder? Few of the participants make to increase the voice. If possible, please. Could you please?
Yeah, sure.
Thank you.
Yeah, sure.
Thank you. Thank you.
Yeah. Okay. Is it fine now?
Yes,
Okay.
Praveen. Yes, yes, sir.
Okay. Okay. Thank you. But when you consider behind the movements of Earth and Moon, so obviously, even in 10th century, even in first, second centuries, people might have known there were other planets like Jupiter, Mars, or that, because these planets are visible even for a naked eye. So, so there arises a quest for what are these planets, and what are their futures, something like that. One of the first person to offer his thoughts on such a matter is Aristotle. He has influenced the scientific community for over 1,000 years, and he mentioned he give a picture like a geocentric universe. So in which world is the center part of the universe, and all other stars like moon or sun or revolving around the center of sun, revolving around the earth. So he also believed that the entire universe is made up of five compounds, like air, water, fire, space, and something like that. Uh, but what's the interesting thing is he believed that planets and stars were perfect spheres, so that they revolve around the Earth. But he thought that Earth might be a plate-like structure, so we could visible in the surface these spheroids running around us. But even in those days, within 200 or 100 years, people understand some discontinuity or something is missing in his picture. One of the thing is that based on Aristotle's picture, we cannot properly define the movement of the planets. So that mm, So Ptolemy comes with the combined star movements, so have made some predictions to the movements of the planets. So what he did was he considered the movements as epicycles, so that all those planets revolve around the smaller cycles around the Earth. Even though this is not true, and this is a flawed view that has that have been accepted for many centuries, since it is one further step from that of Aristotle. But the real or some of the important work arises when Nicholas Copernicus suggested that sun could be the center of our system, and our world is or our earth is revolving around that sun. So he used a telescope and he used his naked eye observations to measure and record different sets of star movements as well as the planets movements, and based upon his ideas, he proposed that sun should be the center part of our system, or earth is revolving around the sun. But this opposes the view of how to say, many people didn't around agree with these studies, and followers of Copernicus are supposed to act secretly, and they have been called as Copernicans. So the finest thing, or the very big breakthrough in terms of astronomy has been made by Galileo Galilei. You might have known some of his experiments, like he put a ball and something like a cotton from the or a bird's feather from the top of the Pisa Tower in Italy, and he proved that ball and actually the story is something like he dropped a coin and ball from the top of the Pisa Tower in Italy, and he proved that both reached the surface at the same time. But there is no evidence like he did such experiment. But there is an evidence for an experiment, something like he allowed to roll balls of different masses in a slope. Of course, this is just something similar to the one I briefed earlier. So even in a slope, the acceleration due to gravity gradually increases, and this almost mimic the mm, uh, falling of ball from a higher height. The this part is interesting because it is easy to measure at a certain time interval how the balls cross, something like that. So he proved even with different masses or with different weight, the acceleration due to gravity is same. Also, one of the important achievements of Galileo Galilei is he devised a telescope that could enlarge the objects up to 20 times. He is the one first discovered there is some satellites around Jupiter. This almost shake entire scientific community as well as the religious people of his time, because the people in those days believed that all the things have been made for humans, and something like that. There were another planet with some other something with satellites is unbelievable for those people. So he have been sentenced to lifetime prison, lifetime sentence in a jail. But his ideas have been understood by some other scientists like Sir Isaac Newton, and have been developed over the next 300 or 400 years. So one of the person who have been made a significant contribution similar to that of Galileo is Kepler. What he devised is he proposed elliptical orbit of planets. So because when you look into the mm, uh, spots of Mars as well as Venus, by using plateaus or Ptolemy's picture, we cannot exactly predict the uh, path. But on the other hand, if you because they have assumed a circular path, they said the distance is unchanged between a planet and the sun. On the other hand, Kepler proposed something like an elliptical orbit, so that the movement of any planet can be predicted very accurately, and this satisfactorily explains why there is a and why there are different seasons at different periods during an year. So these have been very minor improvements compared to what have been achieved by Sir Isaac Newton. You might all have known his contribution as the three laws of motion. Any physics graduate might have gone through his classical dynamics as an elementary course during their undergraduate. Um, but that signifies a very important aspects in the understanding in our understanding of a universe. He proposed something like an universal gravitation, because any object or any matter in space attracts other particle um, in that near to that. So he proposed the inverse square law of gravitation. I hope you might have all known these things. So, what's the significance of such a theory is he proposed there is a no need for a center body or something to be center of the universe. So if everyone has its own mass and everyone has the role of gravity, so everyone act upon its own gravity, and due to that different paths and different planetary motion can be explained, so that there is no need for heliocentric or geocentric theories. So that this revolutionized the idea of our understanding towards universe, and his theory satisfactorily explains almost all the planetary motions, as well as it has been applied to variety of real world physical problems too. On the other hand, uh, in the meantime, people believe that light is something like particle. It is very fast to measure, or its the speed is infinite. But there is a significant mm, identification or discovery by Romer, that while investigating the Jupiter's one of the satellites IO, he found that it took the satellite to hide behind the Jupiter at different time intervals. You just imagine, since the Earth is moving around the elliptical path, the distance between the Jupiter and the Earth varies over the year. So when the Earth is near to the Jupiter, the time taken by the satellite height behind the Jupiter surface is minimal compared to the time taken when there is the maximum distance between the Jupiter and the Earth. So based upon his estimation, he proposed velocity for light, and which is almost correct. The error percentage is around 10 to 15%, but at his time it is very significant invention, discovery, and that proved the thing that light has certain velocity. This has been further improved by James Clerk Maxwell. What he did was, there were certain theory for electricity, and there is a certain theory for magnetism before his time. What he did was he combined all those theories and proposed a new way to approach these theories. And he mentioned, or the combined theory is called electromagnetism, and he mathematically showed that light is an electromagnetic radiation that uh, alternate waves moves through the space, mm, to carry information from one place to other. So this is an important thing that have that contribute both quantum mechanics as well as ancient theory of special relativity, which we are going to see in the next slide. So, but when we consider light as a wave, there is a question, because people extensively know sound travels through the medium. So they thought there might be an medium for light too. They named it as an ether. So in the early 19th century, Michelson and Morley proposed an experiment to discover the velocity of Earth through the luminiferous ether. To the surprisingly, they didn't find any ether, and the velocity of light at any point at any season at any point of the Earth is same, irrespective of its position. So this proved there is no such need for ether uh, for the light to travel through the medium, or travel through the space. Um, Travel through the space, and we know that. Light has a certain speed to that. Light has a definite speed. So combining these aspects in 1905, you might have all known the special theory of relativity was proposed by Einstein, and he argued that events not only the space that as proposed by the Newton, time is also irrelevant for a non-oscillating observer. So his famous equation showed energy and mass are different aspects of the same thing, and they are interchangeable. One of the thing is frame of references which have been uh, entirely changed our understanding of the universe is a frame of references, because if we play a ping pong ball inside a moving train, you don't get any variation in the motion or dynamics of the ball, whereas for an observer outside the train might have see that the ball is also moving with the speed of the train, and it's have been gradually an elliptical like path have been observed for a non-oscillating observer. So that this means um, uh, time is time is also relative, and this introduces a new concept called space-time. Though it's a mathematical model, it has been also known as Minovsky space, which have been proposed by the Russian scientist Minovsky. Uh, for an observer, the particular event will be look like a single photonic dot or a single dot. So this that particular light will have a post, and we call it as the post light cone. There should be a history for that entire particle, as well as the future light cone. So it would have a future. It travel across the space for an infinite amount of time, and this could be understand if we consider our sun and earth. For the distance between our sun and earth is in terms of light is 8 minute distance. For example, if there is a light particle arise from the surface of the sun, it would take 8 minutes to reach the an observer on the earth. In case suddenly if the sun disappears immediately, we would have known only after the 8 minutes. So this explains how an event have been gradually varying with respect to the same space-time. And Einstein argued that the entire space-time have been filled with a lot of light cones. So each and every event in universe is connected to a light cone, and the entire space time have been with using four dimension. We could explain any event in the known universe. But what that special relativity is for non-accelerating observers. So what happens when there is an acceleration? Because a special theory of relativity put a restriction that from the E is equal to mc square, um, no particle or nobody in the universe can travel faster than that of the light particles or the light ray. So since there is the restriction for that, what would happen when we approach the speed of light? As it asked by the special theory of relativity, greater the speed, more would be the mass, at the maximum speed, that's the speed of the light, the mass of that particular traveler would be infinite. So it is hard to explain what happens for an accelerating observer. For that, Einstein proposed thing called general relativity, in which he argued that energy and momentum uh, of the matter in a space-time induce a curvature in the space-time, something like this. So if there is more mass, there would be the higher, there would be the deeper the curve, and for the small mass, the curvature would be the small. This is very significant because it satisfactorily explains several things like the deviation in the slight deviation in the planet's movement, like Mercury, which is very nearer to the sun. Due to the heavy gravitational force, it has a slight deviation in its planetary motion. So that those things have been satisfactorily explained by general relativity. Also, it has some other important aspects too. So one of the main postulates of general theory of the relativity is gravitational lensing, because if there is a light from a distant star is crossing towards the very dense subject, there should be a gravitational pull, and for a distant observer, it could be like a bending of light rays in that region. Some people might have seen such a thing in the famous film Interstellar, but it has been experimentally observed by 1927 by the famous experiment by Eddington. What Eddington did was he measured a light ray from the distant star uh, during a solar eclipse, and as predicted by the general relativity and as predicted by the deviations with the general relativity, it has been exactly the star's path have been deviated. So these are the one of the earliest proof that mm, relativity could be very see, even though it is not a theoretical model, it would be very powerful in terms of theoretical physics that have been proved by this experiment. So another postulates of another one postulate of general theory of relativity is that time moves at different speed for different observers. For example, if there is a um, high dense objects like the Earth, the time moves slow here, and when we move away from this gravitational field, the time moves slower for such an observer. So you might have known the twin paradox, something like that. There is a twins, and one twin is kept in the earth, and another one twin is have been ported to a rocket and sent to the space at the speed of light. After some years, if the twin in the rocket returns to the earth, he might have viewed that person in the earth is much older than his than the person visited the space using the rocket. So there is no actual way to experiment this one. But what scientists devised is, and they placed two atomic clocks at different heights, something like one in the mountain and another one in the a very bottom level of the earth. And they have, since the atomic clocks are very minute, they have observed a very minute deviation in the speeds of the clocks. So one of the very interesting and very uh, important aspects of the general relativity is it satisfactorily explained gravitational redshift. So I think it's around 1920s, Edwin Hubble recorded different galaxies using his telescope. So you might, for an astronomer, even though the galaxy is different, there could be same kind of stars. For example, if the mass and the size of the star is same, they should emit the same kind of radiation even in the different galaxies. But what Hubble observed is that uh, even though they emit the same spectrum, there is a redshift in the spectrum of the galaxies that are much distant from that of Earth. So this is very striking discovery because this means if you know the Doppler effect in sound, we could say that that redshift is due to the fact that that particular galaxy is moving away from us. This put forth a new kind of knowledge, something like that universe is expanding. Up to that time, no one thought like that universe is expanding. People thought like, yeah, there is a solar system, there is a galaxy, and there are tons of galaxies. They combine to form a universe, but no one thought the universe could have expanded. Even a general theory of relativity itself postulate something like that universe cannot be stable for a long time, and there should be something like big bang should have happened. So this gravitational redshift is an evidence that if the planets and galaxies are moving, this means the universe is expanding. If the universe is expanding, there should be surely a starting point at which from that point the universe starts to expanding. Uh, so uh, Fredman, one of the finest scientists of his time, proposed that if there is the starting point, something called Big Bang, the temperature of the universe should be very high. So, with the gradually increasing time, uh, the te- uh, the temperature of the universe have been fall down, and uh, mm, this favors the production of different particles, and which leads to the observation of our current universe. So to support his discovery, in 1950s, Penzias and Wilson discovered a cosmic microwave radiation using a telescope. So they argue something like that. At some point, they observed some microwave radiation from unknown source. So they initially thought like some that could be from an much intelligent organisms than us, but what is the thing is that at the different positions at different points, the radiation is very uniform, even in the space, or even in the poles for different parts of the earth. The intensity of the microwave radiation is very uniform. This indicates that this is the characteristic of the universe, and these radiations arise from the early universe, and it has been accepted as the important evidence for a hot early universe. So this ultimately leads to the conclusion that the universe has a certain beginning, and if there is a beginning, it should have a certain ending. So there is a threshold value. After that, the universe will stop expanding, or it will reverse the process. Something we term it as the Big Crunch. For their work, Penzias and Wilson awarded for a Nobel Prize. Considering the Big Bang theory, by estimating the size of the universe, scientists estimated like the Big Bang may happen some 13.77 billion years ago. So, what happens before the Big Bang? We don't know, because general theory of relativity predicts that before Big Bang, energy, mass are infinitive. So mathematics cannot handle infinite numbers. Also, time is only begins with the Big Bang theory. So prior to time, beginning of time, there is no meaning for speaking about the things before Big Bang. So at the point of Big Bang, there is a enormous energy have been released, and a lot of particles and antiparticles have been produced due to the inflation and quantum fluctuation. So there is an afterglow light pattern should have arisen 3.75 lakh years, which is the one we observed currently as the cosmic wave radiation. So then there were the dark ages. At that time, the universe is expanding gradually, and its temperature is gradually reducing. So you might have known the laws of thermodynamics. When the area increases and the pressure decreases, when the volume increases and the pressure decreases, obviously the temperature decreases. So at the particular temperature, universe favors for the formation of particles. So since universe is arise from the nothing, the amount of particles and antiparticles could be saved. So they might have interact with each other and burst out into light, but somehow number of particles have been more, and these energy particles combined together with the less temperature form electrons, then proton, and a single hydrogen atom have been formed, and the hydrogen atoms start forming a cloud due to their own gravitational pull, and they form like a glued hydrogen ball. So this ball, due to its own gravity, starts nuclear fusion at certain point. That's the birth of the actual star. The we could see the birth cycle of a star in later slides. So that's how the universe have been proceed over those years. Before moving to our next section, let's see the Newton's theory and the determinism, uh, the general philosophical term determinism. What Newton's theory generally mentions is if you have a particular equation and you substitute the particular value, the result should be always same. This is true up to general relativity. If you have a particular set of values for a particular time, if you extrapolate or interpolate, you could have a observe or you could get the present or future events by the same theory. But this is not in the case for the observed universe. Many physical events not agree with it, and determinism is something like this is have been widely believed by scientists in the 19th century because they thought there is no need for god. If we have a particular set of theories, everything can be determined, everything can be done without the intervention of the third or a divine power. That called as a determinism. But a big flaw or a big shudder have been imposed when the quantum mechanics arrived. So the need for quantum mechanics is due to blackbody radiation that you might have studied in your graduation studies. The thing is, if there is a perfect black body, whatever be the radiation we send to that black body, it absorb all kind of radiations, and it emits only radiation that depends on its temperature. Higher the temperature, more would be the frequency. If you bring that theory in the case of real world, if there is an if you put a black body in the space and there is an enormous radiation faults on it, and the falling information gradually increases the black body's temperature, so that ultimately at a certain point it would emit only the ultraviolet radiation at a very high frequency. But this is not true, and in the real world, no such body we have been observed. To explain this paradox, Planck devised the quantum theory in which he argued that energy is emitted and observed as quantas. Those basic things you might have uh, already known. I'm skipping those basic things. But this paves the way for our understanding of basic particles. One thing that have been satisfied. This theory is often called old quantum theory, and it fails to explain the Young's double slit experiment. You might have known this one, probably some undergraduate lab has this experiment. If you send a light wave through the two slits, you would have observed alternate dark and bright fringes. The interesting thing is, if you send instead of light like electrons or neutrons, you could have get the same kind of patterns. We may think due to the ray of particles that alternate fringes have been observed. Uh, if we even send if we devise an experiment at the point that we could send only one electron through the slit, we could expect the electron should go in either one of the slit, and we could have observed a minimum at one near to the through the one slit and maximum at the other slit. That is our expectation. But actually what happens is, even in that case, even if there is a single electron go through the double slit, we still observe alternate dark and bright fringes. Indicates that means something like electron is simultaneously going through the two slits. This have been greatly affects the quantum nature of the uh, quantum nature as proposed by Planck. In order to explain that, we need a wave particle duality. So, at certain point, a particular particle acts as a wave at certain point, and it acts as a particle at certain point. These things you might have known well, but this This wave particle duality created a very interesting phenomena that have been leads Heisenberg to propose uncertainty principle. For example, if you want to measure of an atomic particle, for example, in the microscopic world, the wavelength of the light is much smaller than that of the microscopic things and as well as the macroscopic things. But if you look into the things or particles that are as much as in the size of an atomic particle, their size and the wavelength of the light is almost the same. So if you want to precisely measure the size of the that atomic particle, you could have used the light wave of more frequency. What would happen is you might have measured the size of the particle exactly, but it would cause it would increase the energy of that particle, so that there is a variation in its position due to the it absorbs that light, and obviously it increases its speeds. In case if you want to measure its position accurately, you have to you supposed to use sorry, for example, if you want to measure its momentum, you have to use a lower wavelength. In that case, the wavelength of the light is more than that of the particle, so you could have there is an error percentage in the size determination. So, such a proposal theory induces a very big slap to the deterministic theory as proposed by the Newton. So, for a long time, this was not accepted by humans, and a very famous quote by Einstein: "God never plays dice." Have been due to these kind of issues. Uh, when we have this uncertainty principle and combining the wave particle duality, we could have satisfactorily explain an single atom. Which is what Schrodinger tries to explain. So there is an electron and protons and combination of neutrons and protons form a nucleon, and electrons are revolve around this nucleus, as like the planets revolving around the sun. This have made significant effects by like Niels Bohr and other nuclear physicists have been contributed this much. But one interesting thing is that people uh, it is possible for after 1950s, it is possible for scientists to break even neutrons and protons. So then there arises the question: what made these breaks? Like we know atom is made up of nucleus, and the nucleus is a combination of proton and neutron. And what made that proton? So far that there is a proposal something like quarks, which have been later proved experimentally. So there are three kind of quarks, and the combination of quarks have been used to model the proton and electron, something like that. Just leave these Gauge bosons and Higgs boson. Just look into the quark generation. You could have a up, chomp, top, down, strain, bottom quarks. By using the different combinations and different spins of these quarks, we could design different kind of particles like proton, neutron, antiproton, antineutron, something like that. Um, the one important thing in this case is particle spin. So this explains particles like half spin or individual half spins should follow Pauli's exclusion principle. So those things are called fermions. They are the mass carriers, whereas there are some particles those have integer spins. They always don't follow the exclusion principle, something like photons. They are called as bosons. So there were different theories. for fermions and bosons. I just skip for the sake of time. So combining all this knowledge, scientists proposed a standard model of particles. So there are two kind of particles. As I mentioned, one is called fermions. They are the matter particles. They are the water. Uh, they are the particles or the basic building blocks of any matter. And another one is bosons. They are the force carriers. For example, if you take the gauge boson, something like gluons, it transfers energy between two neutrons inside an atom. And obviously, you might have known about Higgs boson. That is the one gives mass to all the particles. So something like that. Another one well-known boson is photon that carries light over the space. Considering fermions, something like quarks, they made protons and neutrons, and something called electrons. Obviously, electron falls into this field. So this obviously explains uh, both form of the universal. So one is energy and another one is matter, and this standard model almost satisfactorily explains how matter is produced in the universe and how energy is transferred between them. And we know from special theory of relativity, energy can be converted into mass and mass can be converted into energy. Due to that, this using the standard model, we can satisfactorily explain how different particles annihilate and form energy, something like that. By combining this thing, some 3.13 billion years ago, there is a big bang that produced equal amounts of matter. Since every particle, if we look into that standard model, every particle have its own antiparticle. For example, if you look into electron, it has an antiparticle called positron. Similarly, for a neutron, there is an anti-neutron. For quark, there is an anti-quark, something like that. As we combine this knowledge to the Big Bang, equal amount of matter should have produced at the time of Big Bang. Since every particle has an antimatter companion, when the universe is expanded, there is a great possibility of matter and antimatter to interact, and they burst into light. But somehow this is not true, and it seems there is a more number of matter than that of antimatter. So that's why we have why we see today is our universe is entirely made up of matter rather than of antimatter, and this is one of the greatest mystery of modern physics. In order to explain that, let's look into the CPT symmetry, that is a charge, parity, and time symmetry. It is expected that all the physical laws should obey CPT symmetry at any time. For example, if you reverse the charge of a particle, for example, if you replace a charge uh, of an electron into a positron and replace its parity and time, it should behave as that of the actual electron. But later in 1970s, experiments have shown that especially in the experiments with mesons, have shown that quarks and anti-quarks have been uh, produced by exchanging the anti-mesons. The production rate is not uniform, and quarks produced in the higher rate than that of the um antiquarks. This, even though this shows the breaking of CPT symmetry, this explains why there is a more matter in the universe than that of the antimatter over time. Let's look into that life and death of the star. Uh, we have seen that when the hydrogen is condensed to form star, depending upon depending upon the size of that condensation, we could either term it as a massive star or an average star. What would happens to a massive star is initially there will be a fission reaction between that hydrogen atoms. This would create a lot of heliums. After all the hydrogen have been burned out, these heliums start to interact with each other, and they tend to form a more higher level elementals. At that time, it would look like a red supergiant star. So this star would starts to expand very rapidly to stabilize its gravitational pull. Obviously, that would lead to a supernova kind of thing. The star would burst out all the heavy elements on its core, and it either would form a black hole or it would form a neutron star. So, for black hole, we would see the thing in detail in the following slides. Neutron star is nothing but a heavy star that is emits the pulse like things. You might have known the pulsars, star pulsars. Due to the this would have a very strong gravitational pull and emit radiation from their surface. In the case of average star, the similar kind of thing would happen. So after the fuel of the star have been burned out, it would form a red giant star, and using this thing, the star would form a planetary nebula. Something like all its heavy elements will form a nebula and burst it out to form either a white dwarf or black dwarf. Black dwarf and black holes are different, and we would see those things in later. The black hole is a very interesting thing because it is one of the postulates of very interesting postulates of both relativity as well as the quantum theory that shows the singularity in the space time. So this is an advantageous if you look into the if you wish to understand the Big Bang theory. Probably black holes would be the better starting points. Any black hole should have a three layer. One is the outer and inner event horizon, and at the end there is the singularity. So there is no space or time in a singularity, and in the event horizon there is a um, cloud like or a layer like structure in which from which it can emit radiation. So there is a limit called Chandrasekhar limit, which puts the which predicts what kind of stars would form a black hole. If the mass of the star is less than that of the Chandrasekhar limit, it could either form a white dwarf or a neutron star. Whereas if it exceeds the if it exceeds the Chandrasekhar limit, obviously it will leads to the formation of the black hole. Black holes have been extensively studied by Penrose and Stephen Hawking. Um, he mentioned something like that general relativity at any point general relativity doesn't take into the account of quantum mechanics. He thought like something if we unite both the quantum quantum theory as well as general relativity, we could have something like a theory of everything. Since he showed something like singularity at the universe origin, there is a need for quantum gravity because all other fields, something like the strong nuclear force, weak nuclear force, electromagnetic theory, everything have been quantized and fall into the standard model explained very neatly. But gravity alone have been missing in this picture. So he argued that something like we need a theory called theory for quantum gravity. But there is some paradox, especially that arise due to the second law of thermodynamics. It states that the entropy or level of a system is always increases. So our universe is entirely closed system. As the universe expands, the entropy of the universe is always increasing. Each and every matter contains entropy. So if some matter falls into the black hole, what would happen? Because Stephen Hawking predicted that nothing can escape from the black hole. So if the if more and more particles with higher entropy falls into the black hole, it obviously leads to the reduction in entropy of the overall entropy of the thermodynamic, overall entropy of the universe. That obviously leads to the failure of second law of thermodynamics. But later, one of his student Bengenstein proposed something like that. Black hole hides its singularity with a boundary called event horizon. So every time something incident on the black hole, the overall event horizon grows. So Bernstein suggested something like to preserve the second law, the area of the horizon is itself a measure of entropy. Even though Hawking initially not agree with these ideas. Later, he agreed with it, and they developed something called Bekenstein Hawking entropy equation, which is the one Hawking asked to have engraved in his tombstone, which is a very elegant equation because it represents ultimate mashup of physical disciplines. I know a lot of physics students are mentioning is equal to mc square as the base equation or the famous equation in physics. But particularly to myself, this one is the a very beautiful equation. It contains Newton's constant, which clearly relates to gravity, and it has Planck's constant, which relates to quantum mechanics, and the speed of light, c, and that's the talisman of Einstein's relativity, and Boltzmann constant, the herd of thermodynamics. So almost all the major things have been followed into this equation. This shows the idea of Hawking's theory of everything, and this presence of diverse constant hinted physics can be unified at certain point. But this is not always as much as easy because there is an paradox, something called black hole information loss paradox. Hawking suggested that nothing can escape from a uh, black hole. But ultimately, when something falls into that black hole, it would increase the entropy of that system, and obviously that would increase the temperature of the system. So if black hole can radiate, they will eventually so if we consider black hole can radiate due to the falling of different bodies into it, they will eventually evaporate and disappear. So what would happen to the all information that fell in? Uh, does it vanish too? That is because information loss is not predicted by any physical theories. If so, it will violate the central tenet of quantum mechanics. On the other hand, if it escapes from the black hole by somehow, it will violate the Einstein theory of relativity. So ultimately, this is the reason why people think like this is the starting point where either general theory of relativity or quantum mechanics, quantum theory should be either one is correct because both explains the happenings of universe elegantly. Quantum theory explains all other three forces, excluding gravity, whereas relativity takes care of gravity and explains the massive universal fields in the different parts of the universe. So this is the this paradox induces the great one against another. Um, Interesting paradox is we know entanglement between particles. So when the pairs of particles and antiparticles come near a black hole, each pair have a connection called entanglement, and we assume two imaginary persons. One we call as Alice. She have an antiparticle, and there is a person who called Bob. He have an particle. If suppose Alice fall into that black hole, what happens to that entanglement? Bob would see once Alice fall into that black hole, the entanglement have been broken and there is no connection between particle and antiparticle. Whereas for Alice, the connection between, since due to the singularity nature of the black hole, the connection is infinite over time for Alice. So who is correct, whether it's Alice or Bob? That's we called as the Hawking's paradox. So both it is not possible, so far it is not possible for us to unite both so it is not possible for us to devise a theory for quantum gravity, as well it is not possible for us to combine both general relativity as well as the quantum mechanics. And these are the paradoxes, black hole paradoxes, which we cannot explain satisfactorily. So over the in the following, in the last 2 to 3 decades, there is a theory called string theory, which have been expected to explain each and everything of our known universe, as well as the paradoxes that we encountered before. So instead of the string theory proposes something like the fundamental particles are made up of not point-like charges. Instead, there is a tiny strings of in the two-dimensional space. So the infinite combination of the strings forms different particles, and ultimately this leads to our known universe. It predicts that there are extra dimensions to space beyond the obvious length, breadth, and depth. That is obviously the space-time, but we do not experience them because they are bunched up in tiny spaces. The two main limitations of this theory is it doesn't take gravity into its picture, or it doesn't satisfactorily explain the black hole paradoxes. But scientists very strongly believe that this is the obvious way to go towards the device quantum gravity. So there will be an ambiguous and one-to mapping of string picture onto the universe we observe. Uh, if we make the judicious choices, we can get both general relativity and the standard model out of the string theory. So at the end of the at the end of this talk, I wish to finish with principle called anthropic principle. So it states that this is the possible explanation for the question why. For example, we can explain each and everything, when, what, something like that. This is uh, but we cannot answer the question for the questions why. For example, why humans exist, why solar system exists, why there is an universe, something like that. So anthropic principle is the way to address these why kind of questions, because this states that the universe is exist, or the humans are exist. That is the reason why people asking the questions why. So this is a bit complex, and if you see that the known universe, which is the 3 plus 1 direction, which is due to the reason why, which is due to the reason only in that dimension humans can exist, or intelligent creatures can exist. There might be extra dimensions, but those things wouldn't favor humans to exist. So there is to kind of anthropic principle. I just skip those things, but By combining all this knowledge, we come to our final question: is there a room for God? Do we need some divine spark to explain all the happenings in the universe? With the laws of physics, we can explain each and every aspect of the universe, um, even though it is not possible for us to completely understand the things, we can explain every aspect of the universe. So quantum mechanical fluctuations can produce the cosmos, and by if it is possible for you to twist the time and space in the right way, you might have create your own new universe. It is not clear whether you get into that universe, but obviously you can create it. The origin of the laws of physics is still a mystery now, because as I mentioned in the previous slide, if you ask the question why there is a physical law, why there is a certain law, or if you ask why one exactly equals to one, there is no particular meaning for that, or we may never able to solve that one. So as quoted by the physicist Filipino, the divine spark was whatever produced the laws of physics. And I don't know what produced the divine spark. So let's just leave it to the laws of physics. These are the some references. If you really want to get deep into that subject, this is my favorite book, Alice and Bob Meet the Ball of Fire. It has been published by MIT Press. And another thing is, this is the last book by Stephen Hawking, Brief Answers to Big Questions, in which he very deliberately argued that there is no need for a divine spark for the creation of universe. And Corpus Beyond Einstein, as well as Super String Theories, are very nice books to read. Some other books like Black Hole's Order of Time, Death by Black Hole, or a few books you can consider to look into this subject. But the end of the day, thank you. Thanks for your patience.
Okay. Is there any questions from the audience side? Sir, only one question.
Yeah, sure, sure.
First 9, then 8. How many planets are there in the solar system? What was there before Big Bang?
Yeah, that's what I mentioned earlier. If you ask the question, what was before Big Bang? Time starts only at the point of Big Bang. So prior to that, there is no time. So the question is meaningless. What happens before the Big Bang? Because there is no time or no space at the before Big Bang. The question is meaningless at that point. Another thing is, what you asked is solar system, something like you have something for us system. What's that?
First, we said 8 planets, sorry, 9 planets. Now
Uh-huh.
we see 8 planets only.
No, no, no. Actually, those are just for our understanding, because mm, we define something like if it is a planet, it should have a definite path and it shouldn't be affected by other planets. So it should be independent, something like that. So depending upon that mass and that planet's path, we define so we obviously removed Pluto from that phase. It is a dwarf planet. Now we have defined it as a dwarf planet.
Okay, sir. One more question, sir.
Mhm.
Why was Pluto was not a planet, sir?
Yeah, that's the same thing. It has its mass is not less, and its path is not obviously a planetary path. That's the reason.
Okay, sir. Thank you. Vote of thanks. A very good morning to all. It gives me an immense pleasure to deliver vote of thanks for this webinar to all dignitaries and 150 active participants. First of all,
I would like to thank our chief guest, Dr. P.A. Praveen, who honored this webinar with his inspirational speech. Thank you, sir, for your exemplary speech and provoking information to the audience and making the webinar knowledge-based scenario. I am so glad to thank our Honorable Secretary and our beloved Director, Mr. R. Durairathinam, sir, GTN Group of Institution. I would like to thank our most respected principal, Dr. P. Balakurusamy, sir, beloved vice principals, Dr. Chakravarti, sir, Dr. Nadarajan, sir, beloved HODs of physics, Dr. Lalita, ma'am, Dr. Jayaraman, sir, organizing secretary, Dr. R. Jyotimurugan, sir, organizing members of physics of both streams, technical supporters, participants from all over the world. Thank you for one and all for making this online webinar as a grand success. All participants can get e-certificate soon. If you have any enquiries about certificate, please only text on Telegram group. Please don't send any private message. Thank you. Once again, I thank one and all present here. Thank you.